So let us discuss in this video FIR filter design using frequency sampling technique. Okay, so the technique which we studied earlier, it was called as windowing technique. So now let us see how this frequency sampling technique is different from the windowing technique. So what did we do in the windowing technique, by the way? So here we started with the desired frequency response, right? A continuous desired frequency response, which was ranging from minus pi to pi. We took a period. Then afterwards, we took IDTFT of it to get uh, the desired frequency impulse response. Sorry, the impulse response, which would be usually infinite in length. Which will be usually infinite in length. So to limit its length to a finite size, we use windowing, right? So this HD of n, which was IDTFT of the frequency response, it was multiplied by a window to make it finite length, right? And there, we use different types of windows, Hanning, Blackman windows to avoid, the Gibbs phenomenon. And we had a trade-off between the transition bandwidth and the attenuation in the stop, right? Then again, it was non-causal in nature. So we introduced the shift by factor alpha and we ended up getting a causal finite length impulse response H of n. So that was a windowing technique. Whereas in frequency sampling technique, what changes do we have? So here what we do. So let me tell you once again, we started with a continuous frequency response and we took IDTFT. Okay. And then we ended up getting something discrete, right? So in the frequency sampling technique, what we'll do is we'll start with a continuous frequency response. But for change, what we'll do is we will not, let's not have it from minus pi to pi. Instead, let's have it from 0 to 2 pi. Let's have it from 0 to 2 pi. As you know, the thing is periodic and after every 2 pi, the same thing repeats. So this will be my version for the same desired frequency response from 0 to 2 pi. Then afterwards, this is sampled. This particular frequency response is then sampled, right? Depending on your order budget. If at all you have a budget of order 8, then you go for 8 samples. If at all you have order requirement of 20, you go for 20 samples. So there you have it. So once you convert the data, the frequency response into a discrete format, then you need not take IDTFT. Rather, you need to simply take IDFT. That's that. You end up getting the impulse response, right? So no windowing or anything like that. It should be simple. So since we took the desired frequency response and we sampled it, that's why the name frequency sampling technique. And since the frequency response was discrete in nature, once we sampled it, we need not do IDTFT. Instead, we simply took IDFT. Okay. So that was the method, or sorry, that is the method that we are going to learn now. FIR filter design using frequency sampling technique. Okay. So let us see in a bit more detail. So here, let us see what is this like. So you start from the desired frequency response. Say this is your entire period from 0 to 2 pi. And then afterwards, what you are going to do, you are taking some discrete samples here. You are taking certain samples here. How many samples you want? Now, suppose this total duration, by the way, you can see this, by the way, is the phase. Okay, let's talk about the magnitude first. So since the entire duration is 2 pi, since the entire duration is 2 pi. Now, suppose if at all I take some 10 samples, if at all I take 10 samples, say my order is 10, then the individual interval between the two samples is going to be 2 pi by 10. If at all I take 20 samples, the individual, the difference between the samples would be 2 pi by 20. So the spacing between the samples would be 2 pi by n, and the values occur at 0 degrees, 2 pi by n into 1, 2 pi by n into 1, next one 2 pi by n into 2, 2 pi by n into 3, and so on. So any value, okay, suppose you want to have a kth value, it will be there at 2 pi by n into k. Okay. So anything other than that, anything interesting you see here? One more thing that we want to assume is we are assuming a linear phase because we are interested in FIR filters that give us linear phase. Let me once again tell you, we are not interested in those FIR filters that give us non-linear phase. Okay. So we'll assume linear phase also. So you can see your omega replaced by 2 pi by n. This is similar to the way we derived a DFT from DTFT, if at all you remember. Okay, so here you can see this is my h of k. It's your h of omega. Omega replaced by 2 pi by n into k. Okay, so that's the method. So after getting this, what we have to do for this sampled h of k, we need to take once again for the sampled h of k, we need to take the IDFT. Okay, so what's with IDFT? Now remember, see the what kind of impulse response we want. We want an impulse response that is real in nature. Do you see one particular thing here? The frequency response I had drawn is conjugate symmetric. That means the values in the first half and the values in the second half are equal in magnitude, but they are opposite in phase. Okay, opposite on phase, except for the zeroth location. Except for the zeroth location. You remember this thing, by the way. So this is the conjugate symmetry property of DFT for the purely real sequences. Okay, so that means now since your frequency response is conjugate symmetric in nature, you are going to have an impulse response that is purely real. Okay, you are going to have a impulse response that is purely real in nature. And if at all I take IDFT of this particular sequence h of k, if at all I take IDFT of this particular sequence h of k, so what am I going to get? So you can see here, this sequence, what is the expression for IDFT? 1 by n. The expression for IDFT was 1 by n. H of k, if at all I have to write h of k e to the power j 2 pi by n into kn, right? That would have been the value e to the power j, right? Okay. So here it is e to the power j 2 pi by n. So minus sign is missing because this is the expression for IDFT. Okay. Now what happened here? What happened here? Why he has written a real part and why there is a 2? Remember, so we have studied this one symmetry property of DFT. Whenever the sequence is purely real, whenever the sequence is h of n is purely real, so what's going to happen? You are going to have a sequence which is of conjugate symmetry in nature. You are going to have a sequence of conjugate symmetry in nature. Now, if at all I want to take the DFT of this particular sequence, IDFT of the particular sequence, DFT or IDFT of the sequence, both of them, there is one thing in common. You can see the values in the first half, e to the power j theta is cos theta plus j sin theta, e to the power minus cos theta minus j sin theta. So it is e to the power j theta only, but you can see here the first half values theta are going to be negative and the second half values are going to be positive. So all the sign terms are going to get cancelled. Cos of minus theta is cos theta only, right? So that's what it's going to happen. The cos terms, they add having a factor 2, and the sine terms, okay, because of theta minus theta, theta minus theta, theta minus get cancelled. So for e to the power j theta, earlier it was cos theta plus j sin theta. Now all the cos terms, 2 times they are occurring, they get added up, and sine terms they get subtracted. Okay, that's why we will end up getting the cos term. So cos theta plus j sin theta. The real part is the cos theta. That's what this RE, the real part, indicates. It's just cos theta. And then afterwards, the first half and the second half values, except 0. The first half and the second half values are same. The values simply get added up. So that's why you can see. And then the real parts get added. That's what this 2 indicates. The imaginary part, okay, it gets cancelled. The sine term gets cancelled. Okay. So I hope that should be helpful while deriving this particular expression. So there it is. So we are now ready for a frequency sampling technique. So let us see a problem now. Okay, so here is a regular looking problem. Okay, a low pass filter where he has given the, what is the magnitude of this? Magnitude is 1. Okay, phase angle alpha is equal to, you can see, e to the power minus j omega alpha. So this is my alpha, which is related to alpha equal to n minus 1 by 2, right? Alpha equal to n minus 1 by 2. So that makes my filter of order n is equal to 7. Okay, if they mention it, fine. If they do not mention it, from this I can tell. Okay, so here it was not mentioned, so I could conclude it myself. Second catchy thing here is that they have mentioned the value only till pi, say from 0 to pi. So it's for me to assume the value from pi to 2 pi to be a mirror image of whatever that would occur. So what I have taken is I have taken the value from pi to 2 pi as the mirror image of this particular sequence only. Okay. So why am I assuming that, by the way? So I am expecting a sequence h of n, which is purely real. Remember, if at all you are trying to implement it in lab, you will not get the multiplication coefficients which are complex in nature. You have to have real coefficients only. So now let's get started. So what are the method, by the way? We almost forgot, right? So we have this hd of omega. So now what I have to do is I have to split this particular omega into what? So this total duration is 2 pi. So I have to make it into pieces of 2 pi divided by 7. Okay, I have to make it into pieces of 2 pi divided by 7. So first value will be 2 pi divided by 7 into 0. Second value will be 2 pi divided by 7 into 1. What's that number, by the way? Can anybody tell me what is 2 pi by 7 into 1? Then there comes 2 pi by 7 into 2, 2 pi by 7 into 3, 2 pi by 7 into 4. So maybe the thing that's going to be difficult for me is just to identify wherever it is 0, wherever it is non-zero. Okay, so let me just give this a try. Divided by 360 divided by 7. So 360 divided by 7 for the first value is say 51 degrees. So you can see 51 is less than 90 degrees. So it's fine for me. So it is a non-zero number. So magnitude is 1. Phase angle is going to be what will be this value? This will be e to the power minus j 2 pi by 7. Okay, so this is 2 pi by 7 into 3 is there. 3 is part of your question. You can see here 3 is part of your question. 2 pi by 7 is what I replaced for my omega. Omega was replaced by 2 pi by 7. 3 is part of the question. So it is e to the power minus j 6 pi by 7. First value 51 degrees less than 90 degrees. Fine. Next value, what will be the next value? So 360 divided by 7 into 2, that will be 102 degrees. Now this 102 degrees is greater than 90 degrees, so that will be 0. So what next? So now let us divide this by 3. Okay, now let us wait. So now what was that? 51 degrees into 3, 153 degrees. 153 degrees will be somewhere around here. No, this is also less. Okay, this is also 0. Okay, then what will be the next value? So next value will be 2 into 180 divided by 0, 1, 2, 3, 4. So that will be 2 into 180 divided by 7. Yes, 1 into 4. So that's 205. That's also again 0. Then what next? 5. 257. 257 also is less. 257 is also less than 35 by 2. It's somewhere around here. So the next number is has to come around here. So what was that last number, by the way? It was 2 into 180 divided by 6. 2 into divided by 7, sorry, multiplied by 6, 308. So this number 308 came in here. So thank God. So out of the 7 samples, we could get one origin, then 2 non-zero numbers. Remaining 1, 2, 3, 4. 4 numbers turned out to be 0. Are we considering the value at 2 pi? No. This value is already considered here at origin. Excluding the value at 2 pi, remaining 7 values. So 7 values are yes, 1, 2, 3, 4, 5, 6, 7. Yes, we could get 7 values altogether. See, remember this thing. This value, the value at 2 pi has to be skipped. Okay. So now I think we are ready. So let us see next slide. Did we FIR or not? Yes. Okay. So there you can see the value at origin, then this value. So what will be this value? This value will be e to the power minus j 2 pi by 7 is what omega is replaced with. 3 is part of the question. This is my alpha. And then k. For k equal to 0, k equal to 1, even for this particular value for that matter. You can see here one particular thing. So this is written as k minus 7. Okay, k minus 7. That's what is represented. Why is it so? Because you can see the value here is having phase which is opposite in sign. This phase, you can see these phases. So that is why k minus 7. So this is the 7th value. Okay, k minus 7, k minus 6, k minus 7, and so on. Okay. So here, if at all I substitute k equal to 6 here, 6 minus 7 is nothing but 1 only, and minus sign is going to get cancelled. So it is going to be 6 pi by 7, but there's going to be a plus sign here. That's what is indicated. Magnitude is same. Phase is exactly opposite. Okay. Phase is exactly opposite. Okay. So that's it. Now we are ready. So origin was there. So at k equal to 0, this is anyway 1. So this value and this value is what we need to bother about. You have seen the expression for IDFT, right? So let me just show you that particular expression once again for a moment. Let me just show you that expression for once again for a moment. There's something interesting here. So let me clarify one thing. Wait a second. Let me clarify one thing here by going to the previous. Okay. So you can see one thing I want to tell you. This h of n here is nothing but it is simply IDFT of h of k. But then why we chose to have this particular expression is this is a simpler expression, you can see, because the values in the first half and second half are same except for the change in the phase. We try to optimize it, right? Values they simply add in, and so that's when this 2 came. And you can see if at all I had to directly calculate, you can see now this particular thing here, this is a real part. So I need not do this cos and sine. Okay. If at all you have to do this cos and sine separately, the real part and imaginary part separately, need separate registers. Okay. Need separate register. So this particular derivation and this particular expression is much more implementation friendly and computationally effective. Okay. It's computationally effective. Okay. Or putting this real term here, it reduces a whole lot of number of multiplication related to the complex and the sign term. Okay. Okay. Now let us go back to the question that we were solving. Okay. So here you can see we took the frequency response and then afterwards we sampled it, and here we are ready with h of k. And now, so here you can see we need not to bother about only the first half values. The second half values will be taken care by the expression. So here is this is the case where n is equal to odd. Okay, this is the case where n is equal to odd. Okay. So you can see except for the first values, there are 3 on the left side and 3 on the right from the midpoint. Okay. So you can see 1 by 7 is part of the expression m. Then this h of 0, which is 1, Then first half 1 to 3, which I need not bother because there is only one value. The real part is nothing but, as I told you, it's cos. Then h of k, I need to substitute this value here for k is equal to 1. Okay, need to substitute for k is equal to 1. E to the power j divided by 7 into your 3. Okay, so e to the power, okay, this is the expression, okay, the general expression. Okay, then n into k, n, these values of n equal to 0, 1, 2, 3, 4, 5, 6, 7, n from 0 to less than 7, 6. Okay, less than 7 or less than equal to 6, I can write. Okay, k is equal to what? K is equal to 1 because there's only one term that's going to come in there. Okay, so see, yes, so here you can see this is this was a substitution which also turned out to be 1. Then the real part is nothing but cos. So k is equal to 1. Then here also k is equal to 1, and this is my alpha. This is h of k, whereas this is my part of that IDFT formula. So once you get this particular thing, simply substitute and you shall get something symmetric. Okay, the moment you get symmetry, maybe your answer is right. If at all you're not getting symmetry, somewhere you might have done a mistake. Okay, then afterwards, if at all implementation is asked, how are you going to do it? So you're simply going to take this x of n, h of n, then afterwards you're going to put this d flip-flops, 1 d flip-flop, 2 d flip-flops, 3. Remember this, right? These kind of d flip-flops you're going to take, you're going to add them. How many 1 2 3 4 5 6, and then afterwards the first value and the last value. Okay, for this you need to multiply by minus 0. What is that? 114. Okay, whatever. Then afterward the second value and the last part one value. Here also you need to add this, then this should be multiplied by 0.079. These two again, this needs to be added further, and then afterward this to be added with this, right? The values here on these sides. Okay, so again, what are these things, by the way? Once again, the optimization things, right? The clever use of brackets, I keep telling. Okay, so 3 2. Okay, fine, yes, and then afterwards finally the last term. Okay, so there, so that should be it. Okay, so you can see these kind of implementations, by the way, they are called as this kind of implementation, direct implementation. This is specifically called the name, remember the name, direct form, which is called as direct form 1 representation, direct form 1 representation. Okay, so why I'm telling this, because there can be two types of representations for implementations for filters. One is direct form representations and second one is lattice representation. So once we are done with this particular topic, we are going to go to the lattice representations also. Okay, so that's that. Let me stop here. In the next class, I will be solving one more problem where the specifications will be given in analog form and we have to convert the data into digital and design a digital filter. Okay, so bye.